In this problem, we have a drill that's oscillating a string, making a standing wave. We want to know what speed does the wave propagate through the rope, so we'll use our wave speed equation, V equals F times lambda. Now the frequency of the rotation of the drill is 20 Hertz, and the wavelength for a standing wave, this is one wavelength, starting from a node to the next node to the next node. That is one wavelength. So the wavelength here is 3 meters, making our wave speed 60 meters per second. A student predicts that decreasing the mass will decrease the tension in the rope, which decreases the speed at which the wave travels through the rope, decreasing the wavelength of the wave, increasing the number of wavelengths that will fit in the rope. But when the student reduces the mass, no standing wave forms at all. Explain what aspects of the student's reasoning were correct and which aspects were incorrect. So let's go through this. If we decrease the tension, it is true that the speed will decrease as well. And according to V equals F lambda, we still have the drill spinning at 20 Hertz, but the speed went down, so the wavelength must also decrease. And so this is a correct statement as well, that the wavelength of the wave decreases. If the wavelength decreased, it would be possible that the number of wavelengths that fit in the rope increased. So I could show you an example of that right here. Right? This standing wave I just drew has a smaller wavelength than the original wave, and so now we had 1.5 wavelengths fitting in that rope. But no standing wave formed, and the reason would be that the boundary conditions were not met. And the boundary conditions for a string tied down at both ends are that you must have nodes at both ends. So when the student began to increase the speed of the drill, they wouldn't get another standing wave until you got to the point where you had exactly 3/2 wavelengths fitting in there. The 5 kilogram mass is now replaced, so we have our 5 kilogram mass back on here, and we slowly increase the frequency until we do get a point where another standing wave is formed. So now that the tension of the string remains constant, we know the wave speed remains constant. We're increasing the frequency, and so the wavelength must be decreased. So we're going to fit more waves in this. And so it would look like this. So in this new wave, we have 1.5 wavelengths fitting in the length of that string. So 3/2 of a wavelength is equal to 3 meters. And so the wavelength is equal to 2 meters. Now we use the wave speed equation. The wave is still propagating at 60 meters per second. And the wavelength is 2 meters. So the drill must be rotating at 30 Hertz.